It's a strange feeling. I'm not working on slides 1 minute before the talk.
And you have some water, Jim?
I have coffee.
Okay,
yeah.
Good. I cannot get you a coffee now. So, okay, great. So welcome everybody to this third day of the Frontier School. And it's a real pleasure to have Jim Hone in the program. Jim from Columbia University does not really need an introduction. He's in the field since the beginning and has made many breakthroughs, including the capabilities to make extremely clean graphene devices. And so all of us can be very grateful to what Jim has done for the community. And we're still enjoying his innovations every day. Jim is Center Director of the Center for Programmable Quantum Materials. You can see the logo here. And he always likes to come to Barcelona. So I'm glad you accepted to give a talk at this school. However, he is at home and the background is not a fake Zoom background, but this is actually really his house. So that's very comfortable. Just one practical note. The way we handle questions in these two talks is going to be like this. So you type the question. You don't do the hand raising because Jim likes to see the questions and then answer them on the go. So please ask questions. This is a school. That means you can ask, don't hesitate to ask any question you want and type them and Jim will answer them during the talk. But also after the talk, we have time for Q&A. Okay, I won't waste more of your time. So Jim, the floor is yours, or the screen is yours.
Thank you, Frank, very much for the great introduction. It's great to talk to everybody. I do wish I could be there in person in Barcelona. It's such a wonderful place to be. But this is the next best thing, and let's make the best of it. So as Frank said, we have a couple of great centers at Columbia. I'm actually the director of the Materials Research Center. Dmitry Basov is the director of our EFRC Programmable Materials Center, but all of the work I'm going to talk about is coming out of these two centers. It's all very, very interdisciplinary. I'll talk about some of the leading people, but these are big group efforts. Okay, so what I'd like to talk to you about today is twisting heterostructures to change electronic and optical properties, right? And let's see if we can get this to work. There we go, right? So, you know, we've been in the business of stacking, putting things on top of other things for about 10 years now, creating these beautiful van der Waals heterostructures. I think the first talk I gave about this actually was in Barcelona in maybe 2011 or something. This has been a wonderful field. We love making devices by and new materials by mixing and matching atomic layers. But as we're all familiar with, especially in this school, the angle of rotation between different layers is also an important thing to control and to manipulate and really take advantage of to further tune electronic and optical properties. And so at Columbia for the past couple of years, we've been thinking about, you know, how do we do that rather than stacking devices one at a time? How do we do this in a more controlled way so we can have explore all of these different ranges of twist angles? You know, so the idea is, can we combine this stacking with manipulating using an AFM, right? And there we go, right? So what we're using is actually a nano manipulation software that comes with a Bruker AFM. So we think about this as the nano person going around on our sample and pushing it and rotating it. All right. So let me tell you about the first simple experiment. So I'm going to talk about hopefully four different experiments, 4 different papers, if we can have time for all of them. So let me start at the beginning. And the simplest experiment we thought about was looking at the contacts between 2 pieces of graphene, and to understand how the contact resistance, just the electrical contact resistance, depends on twist angle. And the idea there is that if you have a perfect interface, then you should not have momentum scattering, at the interface. And then if you have electrons at K point in one layer and another K point in another layer, you have a momentum mismatch. And this should strongly suppress interlayer tunneling. So here was the simple approach. So we started by taking a sheet of graphene and just etching it into parallel strips. So we don't know the exact lattice angle, but we know the relative angle these two pieces are aligned. And then we take, it's very hard to do with graphene, but we take a piece of graphite, cut it into a cross pattern, and transfer it on top of these pieces. And then the whole thing sits on boron nitride on the bottom. And the idea is now we can do a 4-terminal electrical transport measurement. We can apply a voltage between these two strips and measure the current just like a normal, or apply current, measure the voltage just like a normal 4-terminal device. And the important thing here is that this graphite, it actually ends up being also covered with gold on top. But this graphite is very, very low resistance. And so the dominant resistance is actually this contact resistance at this point and this point. So here's a 3D rendering of what we're actually doing. And you can see on top now we have these, here's our cross after we push it with the AFM and then scan at different steps. And you can see that we can change that angle, and we can take electrical measurements at different angles, right? And so this is our measurement of the contact resistance as a function of a rotation angle, and this is all at room temperature. And what you can see is just, we can also, of course, vary the gate voltage on to change the Fermi level in the graphene. But if we just look at 0 gate voltage, where we should be near charge neutrality, you can see we get a modulation of more than a factor of 40, almost 2 orders of magnitude change in contact resistance when we change the contact angle. So this tells us a few things right away. It tells us that these interfaces are pristine. If we had a lot of junk in there, that would scramble the momentum information, and we shouldn't see this clear signature of angular dependence. And it tells us that if we want to make very good graphite or graphene contact, that angular control really is important. You also see there are a couple of interesting features here, here, and here. And these are angles where there's partial commensurability between the two lattices. Okay, so let's see. Next experiment. So that was one. We're staying on time so far. So the next experiment is to look at the Moiré pattern between graphene and boron nitride. And of course, we're all familiar with this pattern here. Where's my beautiful animation? There's our PowerPoint animation, right? So we know that as we change that angle, we can change the wavelength of that Moiré lattice. And especially around 0 degrees, we get a very sharp change in the Moiré lattice constant up to about 14 nanometers when we're perfectly aligned. So what we want to be able to do is really, we know that all the interesting physics happens when we have the slightly larger period Moiré lattice. And so we want to be able to do our rotation within just a couple degrees of alignment. So these are STM images of that Moiré lattice. Of course, this is just reviewing. I think everyone in the audience is probably familiar with this. We know that graphene has a single Dirac point, which leads to a peak in resistance at charge neutrality. But when we have a superlattice potential from the Moiré lattice, then we get a cloning of this, the band structure. So we have the primary Dirac point, and above and below, I'm just showing the ones on the whole side, we have secondary Dirac points. And when we now look at resistivity as a function of gate voltage or carrier density, we can see both the primary and the secondary Dirac points. And the peak on the whole side is always higher than the peak on the electron side because of the details of the superlattice potential. One more thing is that when we have this superlattice, it breaks the symmetry of the system. It breaks inversion symmetry, and that means we can open up a band gap. And the question is, you know, how does that band gap change with the period of the Moiré pattern? And how are the band gaps at the primary direct point and these secondary direct points different? So that's the big physics in the electronic structure that we're going to try to explore by manipulating this twist angle. So in this paper, what we did is we use a slightly different structure. We first, again, we build everything on a bottom piece of boron nitride. Then we build a Hall bar out of graphene. And then we etch a piece of boron nitride into this rotator structure. And we put these little extra pieces on there. We call these handles that we can push on and turn, right? So that's the idea. And so what we're going to do is then do, again, electrical transport measurements through this graphene Hall bar. The bottom BN is far off alignment, so we have very little effect of a Moiré pattern from the bottom BN, but then the top BN we can bring into alignment and explore angles near alignment and change that Moiré pattern. Right? So that's what we're going to do. So here's one of these structures imaged by AFM. We use, just to stiffen this boron nitride, we use E-beam resist called HSQ, just as a stiff insulating layer on top. And here is a image or an animation where we do this rotation, and we rotate a little bit, take an image, rotate a little bit, take an image, and then we've stitched these images together into an animation that shows that we can, in fact, rotate. You can see it slides around a little bit, but we can control that by nudging it back into place. You can also notice a few other things. You know, you'll notice that the system is not as ideal looking as it is in the cartoon. There's a lot of junk on the surface because of the polymers we're using to transfer. But you also, I think, can notice, I'm pointing with a pen on the screen, which doesn't do anything. You know, you can notice that the area underneath where we've rotated, so we kind of push the junk out of the way, and the area underneath that rotation is actually quite clean. So these interfaces tend to self-clean, which is really advantageous. Okay, so the first thing we can do, even before we do any electrical transport measurements, is just to look at the Raman spectra. So it's already been established that the 2D peak in the Raman spectrum broadens when we have a long wavelength Moiré pattern. Let's see, two questions. So first is the AFM tip only hitting the handle? Yes. So let me, you know, in the cartoon, what we're doing, if I can go backwards somehow. Right, so we actually, we bring it down into contact with the top BN and then push sideways, right? So, or with this bottom BN rather, and push sideways. So we're only pushing on that top piece. The second question is, does the rotating the top HBN introduce strain? That is still, let me save that a little bit for the final topic where we're seeing some evidence of those types of effects. So we know that when we use a very thin piece of BN on top, it tends to be damaged, you know, especially when we get toward, well, as you'll see in a second, the friction changes with rotation angle. So when we're off of alignment, there's very low friction and we don't need a lot of force, but when we're close to alignment, we need a lot more force. Right, so this is related to, so the third question I got was, do you have to use a thick piece on top? Can you rotate monolayers? And of course, we're all thinking about, you know, why aren't we doing this with twisted bilayers? And the answer has to do with the stickiness. So when you get close to alignment, these pieces tend to stick together. I'll show you some data on that in a second. And when you have a monolayer, when you push it, it ends up buckling and wrinkling rather than cleanly rotating. We are working on ways around that problem. One final question. what's the relationship between the AFM twist and the actual twist angle. So we can program in the twist angle pretty well because we use a kind of a nanolithography software where we can say, you know, move 10 nanometers or 50 nanometers. And we know that that should correspond to a certain twist angle, but we always, we can, you know, we always then image afterward. In some cases, we can actually measure electrical properties while we're rotating, and this is useful when if we're looking at the secondary Dirac peak, we can actually kind of push until the resistance is maximum, for instance. How slowly do we rotate? That I don't remember, but it's generally at the speed of kind of AFM imaging, right? So if you just imagine, you know, we're scanning one whole image at 1 hertz, right? It's, you know, on the order of a second to do this rotation. Okay, so let me get moving here. All right, so here's our Raman data, right? So we can see very clearly that this 2D peak width broadens quite considerably when we rotate near 0 degrees. And the other thing that it really comes out of this is that we can control that rotation angle near 0 to more precisely than a degree, to about 0.1 to 0.2 degrees. That's our error bars here. And so this is very nice. This shows us that we have enough control to do the experiments we want to do. And in fact, if we look at this data, we can plot now the full width half max as a function of Moiré wavelength, and we see this nice linear relationship. This repeats what was done previously, but had to be done on multiple samples. And so when you're making multiple samples, oh, it takes a lot more work, but you also get a lot more scatter in the data because of sample to sample variability, right? So we see this very nice trend that we have a controlled experiment, don't have to worry about that variability. So as I mentioned, we can also look at friction. This is something we're still trying to fully understand, but let me just show you some of the main things. So the first thing, so we look at the friction by the tilt angle of the AFM tip as it pushes the BN. So you get that information automatically by looking at the quad photodetector in the AFM. And you know what we see is that we have a big peak in the friction when these two come close to alignment. And so that's one way of telling us when we're at alignment. And that points to the challenge in you know, creating very thin structures where we want to explore structures very, very near alignment. This friction goes almost to infinity when we have two of the same material, because then you're just making a bulk crystal of the same material. One of the interesting things here is when we just push one of these structures sideways, when we're close to alignment, we see what's called a stick-slip pattern. This is very common in kind of nano friction experiments. But the interesting thing is stick-slip is usually at the atomic scale. And now the characteristic size scale of this stick-slip friction, which you see here, right, there's all of these kind of stick-slip patterns, is actually the Moiré lattice. So somehow the Moiré lattice is giving us stick slip in the same way as an atomic lattice traditionally does. That still has to be understood. But let's go to the electronic properties now. So again, just doing a room temperature experiment. What we can do is now start rotating that top BN toward alignment, right? So we can go from 1.6 degrees where we see in kind of this range, we see almost no effect of the Moiré lattice. And now we start to see the secondary peaks emerging strongly on the hole side, a little bit more weakly on the electron side. And as we go to angles closer and closer to 0, we can really see that both strengthening and moving closer to the Dirac point, right? Because as we change the Moiré period, those secondary Dirac points move closer to the original Dirac point in energy. So we can just now look at this voltage difference, which is basically an energy or a density difference as a function of angle, and we see a very nice simple quadratic behavior which matches theory very well. Right? So this is nice. Again, something that would be much harder to do in a non-controlled experiment, we can do this very cleanly in this experiment. And it shows you the real difference, again, between, you know, Moiré lattice of 14 nanometers versus lattice of 10 nanometers. You can see a dramatic difference in the position of that satellite peak. So now the real heroic experiment happens. So this is all fine. You do this at room temperature. It's you know, not so bad. You can set up the electronics in the AFM. The next thing we want to do is go to low temperature because we want to understand how the band gap evolves at all of these different angles. In that case, what we have to do is push to a given angle, take the chip out of the AFM. So this has to be done all while it's wire bonded. Take it into the cryostat, cool it down, measure activation for the gap, warm it back up, and rotate again. So this takes, so, you know, this one data plot here is a couple of weeks worth of effort going back and forth between the AFM and the cryostat. But at each one of these peaks, what we can do is look at conductivity. Conductance is a function of inverse temperature. We can make an Arrhenius plot, and we can extract an activation energy from this data. And so in that way, we can measure the electronic band gap. Just looking at low temperature, you can see, of course, the resistance is going up as we go closer to alignment, and that's suggesting that the band gap is going up as well. So the interesting thing we find, I think I have some text here, is that if we look at the secondary Dirac peak, it you know, shows this nice kind of regular dome behavior between -1 and 1 degrees. When we look at the primary Dirac point, it shows, you know, roughly a similar dome behavior, although much broader, but it also actually shows all of this zigzag behavior here. And this zigzag is, so just seeing that the shapes of those domes are different tells us that the origins, the kind of the microscopic origins of the primary and secondary Dirac point gaps probably are different. The other thing that is that, you know, this fine structure here is actually reproducible. So you'll see here that these are actually 2 data points. These are 2 data points and 2 here. Those are taken by changing angle and then coming back to the same angle. And we see the same gap. So, you know, this I think still needs more filling in, you know, to really identify what's going on in all of these very, very small angle differences here. Okay, so that's the end of paper number 2. We're halfway through. Let me, how are we on time? We're doing pretty well. Okay, so now we want to ask another question using a very, very similar structure. So as you'll recall, in the last experiment, what we did was we first took the bottom BN, we misaligned the graphene to that. So there's very little, this is a very short wavelength Moiré pattern, there's very little effect of this pattern. Now what we want to do is bring these two into alignment to start and then rotate on top. So now we're going to look at, you know, if we want to do the kind of the full phase space experiment, we could look at changing both the top and bottom angle. We can't use 2 AFMs on top and bottom. So what we're doing is now we're choosing just strong alignment on the bottom, and then we can go in and out of alignment on the top. Right? The interesting thing we'll see here, though, is that there's a difference when we have just a single graphene in BN, 0 and 60 degrees are equivalent. But when we have 2 layers of boron nitride, 0 and 60 degrees are no longer equivalent. And we can see that here from just kind of simple PowerPoint theory, right? So, you know, what we've done here is just colored all the borons red, all the nitrogens blue. And when we stack 2 layers on top of each other, and then the carbon is gray, right? So this actually just this color coding lets us see the symmetry of the system. So when we have the bottom at 0 and the top at 0 degrees, then we get nitrogen on top of nitrogen, boron on top of boron, and we see this kind of red to blue change. And if you trace out where the red is, you can see an inverted triangle here If you trace out the blue, this is a right side up triangle. And so this actually, this structure has broken inversion symmetry, and that allows the opening of a band gap. Now, if we go to the right, if we rotate the top by 60 degrees, now we have a boron on top of a nitrogen and a nitrogen on top of a boron. And that means instead of red and blue, we have purple everywhere. So what we've done is actually restored inversion symmetry, right? So our guess here is that this case should have a band gap, but this case should not. So let's see what we can see. So, you know, we like to see that this is changing the symmetry of the superlattice without actually changing the wavelength or other properties of the superlattice, just changing the symmetry. So we can do a little bit better theory than that. You know, there's very well-developed theory that even, you know, I can understand to calculate the superlattice potential. So you have to look at the real potential variation from being on top of boron versus nitrogen. And then you have to look at the effect of that superlattice on the block states at the K point. And, you know, again, what you see is that if you have both alignment or kind of a single layer, then you have this, you see this superlattice potential. And again, you can see the broken symmetry here. You have this inverted triangle here. When we now do the same thing with the top rotated by 60 degrees, what we see is that now we have restored inversion symmetry. We also see that we have the same strength of the superlattice potential. So it's not that we're just canceling out the superlattice, but we're changing its symmetry. Any questions about that? I think, oh, sorry, I missed a, sorry about that. I didn't scroll down on the, the question box here. Let's see. Let me go back to a few questions. Is there any relaxation after we rotate to a certain angle? Most of the time not, except when we're very near alignment, then things get sticky. Is the Raman done in situ in the AFM? Not, we don't have that. So we do it ex situ, but it's pretty easy. Let's see. So I guess what is the origin of the broadening of the Raman features with lambda? So as I understand, that's basically the superlattice potential acts as a scattering potential, and it allows kind of different types of relaxation, different types of electron phonon coupling. So there is, it's not a simple physical parameter, but that's the origin. So yeah, so the next question is, can we use the AFM deflection to understand what our twist angle is? And absolutely. So I'll show you that in the last talk, that what we can do is we can make identical structures and we can push one until it locks in place. We know that's 0, and then we can measure relative angles of other ones. So do we expect that higher friction at aligned angles is due to atomic reconstruction? I think that's part of it. There's certainly just better commensurability between the different structures. Don't know 100% yet. That still has to be modeled. Why is the behavior not symmetric for positive and negative twist angles? In the graphene boron nitride, it should be at least very close to that. Typical band gap energies are tens of milli-electron volts. So these are not giant gaps, but they're not tiny either. So I had a question about 2BN a lot. Let me get to this maybe in the next talk. So this is a very interesting question. When the 2BN are aligned at 0 degrees, what about translational alignment? So we kind of ignore that. I think if you're thinking in K-space, that doesn't really matter so much. But I think they're also, you can calculate the most stable configuration. So you allow a little bit of relaxation, and that should bring everything back into alignment. What do I mean by the superlattice potential? All right, so this is what I'm doing here. So we're caught up. So the superlattice potential is basically projecting the real space potential. So this is just basically you have a boron, it has some charge on it. So there's some local potential on top of a boron. There's a local potential on top of a nitrogen just because of different charges. It's just a polar material. And so there's basically, U of X varying in real space. But then you have basically, if you think about your electrons living at the K point, those have a wavelength as well. And so those are going to sample this. You're going to get kind of an interference pattern between those, the electrons at a given K point, at a given momentum point, and the real superlattice potential. It's kind of like, sampling music at a certain frequency or something like that. You can get, there's almost like an aliasing of that very, very, atomic scale potential, right? You're aliasing it at the wavelength of the electron itself. And basically there's that interference pattern ends up having the same, because if you think about the Moiré lattice, it's basically the interference between, the graphene lattice and the BN lattice, and you get the same wavelength from the interference of the BN atomic potential with the K point electrons. Okay, let me get to the next questions. Let's see, where are we? Let's see, when we break symmetry, does the Raman peak narrow back? Let me get to that. We're almost there. Does stickiness go down at higher temperature? It does. Next question, sigma. So what about mirror symmetry between 0 and 60? So of course, once you break, once you're not at 0 and 60, you're always going to break some kind of mirror symmetry, but the situation is clearest at 0 versus 60. Can we induce chiral properties? Now you're getting really fun. We're thinking about that. I think there's a lot of interesting things to do there. We're not done yet. Can we ignore strain when looking at the full width half max? I think in this case we can, especially because the top BN is very thick. I think when we have if we want to look at monolayer graphene and monolayer BN, then there's going to be a lot of reconstruction because both are equally stretchy. And so there, we can't ignore strain. We know that in twisted bilayer graphene, strain gradients give us very different Moiré patterns locally. So all of this are kind of higher order effects that, again, with these big rigid rotators, it's not such a big issue, but these are things to look at in the future, I think. And again, if we heat and cool down or do anything, does it seem to change the rotation angle? So in the experiments I talked about, it's amazing actually that we can, cool down to cryogenic temperatures, warm back up to room temperature, and we stay at the same angle. If we look at electrical properties, they're identical. And that's what allows us to do this, to have confidence in our measurements of the band gaps by activation, right? So if we saw angles changing when we cool down and heat it up, then, we would really not be able to interpret our activation measurements very well. Okay, caught up. So let's see now where we are. So again, we have these two, we have a bottom BN, we have a top BN, and we see that there's a difference between 0 and 60, or I like to think about a 0 and 180. That's completely equivalent. So we have kind of aligned and anti-aligned structures. What we see is that the superlattice itself actually, The magnitude doesn't change, but the symmetry of it changes quite a lot. Okay, so again, same structure as before, except with bottom aligned to the bottom, the graphene aligned to the bottom BM. Okay, so this is what we see, more or less from a single Moiré pattern, right? So if we plot the full width half max versus angle without the bottom alignment, so it's not doing, the bottom is not doing anything, then we see basically, narrow peak, and then when we get to either 0 or 60 degrees, we see a strong increase up to about 35 inverse centimeters. Okay. There's the raw data, right? Okay, so now when we align, so if we start here at 0 or 60, or start at the bottom at 0, and now add the top piece, what we see basically is just a rigid shift of this pattern, right? So now if we have a lined bottom, we're still at 35 and the top isn't doing anything. But now when we have a lined, both are aligned, we more or less double the broadening, right? So we get, very broad peaks. But we also see that there's symmetry between 0 and 60 degrees, right? So this is telling us that the broadening of the Raman spectrum is really sensitive just to the magnitude of our superlattice potential and not to its symmetry, right? But this kind of shows us that we are in fact getting a stronger superlattice potential. These are adding the way we think they should. Okay, so now we look at transport. So what we do is we have this, here's my little cartoon. We just do a normal Hall bar measurement. Our rotator is covering the entire kind of channel region of this Hall bar. So we really are measuring a kind of a uniform area. And now we start to rotate like this while looking at the transport behavior as a function of gate voltage. And again, what we see is here's the primary Dirac point that stays in the same place. And we can see this secondary Dirac point moving and getting much larger, right? So when we have the bottom aligned and the top is misaligned, then this is the effect of just the bottom. When we double align them, we see basically the same position of the secondary Dirac point, but it gets stronger, right? So that's the strengthening of the superlattice potential. Now we can go in the opposite direction. All right, so now when we go to the bottom is 0 degrees, the top is 60 degrees. Again, we see this secondary Dirac point in the same place, but it's weaker compared to the point at 0, 0. So 0, 60 is weaker than 0, 0. There are some funny little details in there, but so if now we can plot just the height of the primary Dirac point. So you can also see again, this primary Dirac point is basically back to the place it was. Here it's taller, more resistive. So what we see in the room temperature transport response is if we look at the primary Dirac point, right, it's extra tall at 0 degrees. And the top, it's strongly suppressed at 0, 60, and then extra tall again at 0, 120, right? So we see 120 degree periodicity rather than 60 degree periodicity. We see a similar pattern in the secondary Dirac point where we have identical behavior at 0, 120, and 240, and we have a smaller peak at 60, 180, and 30, right? So that is suppressed to some degree. So again, we can do these painful thermal activation measurements where we go back and forth and we cool down. And we can look at the evolution of these peaks as we cool, and we can see a huge difference here. So if we, again, have this double aligned structure, this structure becomes strongly insulating. When we have this anti-aligned structure, 0, 60 or 0, 180, we see, less than 1 order of magnitude decrease in the conductivity as we cool down, right? So we see, it's a little bit hard to get a really rigorous a measure of the gap from activation. These are not clean Arrhenius plots, but if we kind of do the best we can, you know, as a little bit of a guess here, we can certainly see that there's a you know, dramatic difference in the activation energy between the double aligned versus the anti-aligned structure. And we see the same thing for this secondary direct point. Again, at low temperature, we see, you know, upon cooling, when we're anti-aligned, we see almost no change, you know, just a factor of a few in conductivity, whereas, you know, when we're a double aligned, we see, you know, strong suppression when we cool down. And so this is what we see for the gaps. Again, when our top is off alignment, this is basically the gap that we see from the bottom BN. That's about, in our experiments, is about, in both cases for the primary and secondary, it's about 30 to 40 MeV. When we add a second superlattice potential with maintaining that broken symmetry, we enhance that gap to about 60 MeV. And when we do this anti-alignment to restore inversion symmetry, we suppress these gaps. Now the question is, why don't the gaps go all the way to 0? So let me maybe anticipate that question. Then I'll get to a couple of the actual questions. You know, this is of course our simple model of, you know, perfect contact. So I think in this case, what it's telling us, which is not incredibly surprising, is that we have a little bit somehow better coupling between the bottom BN and the graphene. That's the first part of the stack we make versus the top, right? So if there's any imbalance in those coupling strengths, then you're not going to get perfect cancellation of the inversion symmetry. But we're still definitely seeing strong suppression. Okay, I think I'm good. All right, so let's see. So, you know, then we can turn on a magnetic field and we can try to make some Hofstadter butterflies. And in this case, what we're going to look at then is how do these Hofstadter butterfly, these kind of Landau fans, secondary Landau fans, start to emanate from these secondary Dirac points. And I just, you know, these are already very complicated, so I don't want to go into too much here. But one of the interesting things is that when we make this anti-aligned structure, we suppress the resistivity peak at 0, right? So you can see in this case, when we're double aligned, you know, we get this very strong fan diagram, but it's very hard to get good data near neutrality because you have this insulating peak. So now we've suppressed that gap near charge neutrality and we can get a lot better data near 0. Same thing near these secondary Dirac points. You just kind of get a wash here, but now we can get data much closer to these secondary Dirac points. So that's of some interest. Kind of more fundamentally, that, you know, what we can now do is start looking at, well, what happens if we have Moiré patterns that have slightly different wavelengths? And so, you know, you can do some very interesting fun with graphics here, right? So if we add these two different wavelengths, you can really get some crazy features you can turn into screensavers and things like that. So, you know, how does that all wash out, right? So it turns out that just if you look at the peak positions of the peaks, it's pretty simple, right? You basically see two peaks at the position of where you expect them from each Moiré pattern separately. We also see peaks that seem to correspond to kind of the interference between those Moiré patterns, but those peaks are small and much harder to see, right? So that all makes sense pretty well. So maybe, and then, you know, again, you can turn on fields and see, again, kind of Landau fans emitting from these points. I think the interesting thing comes when you look at the temperature dependent resistivity. And if we have two patterns that are off alignment by about 1 degree, so again, the bottom is 0, the top is 59.1 degrees, when we look at the resistance as a function of temperature, we see that, you know, we have a sharp peak at low temperature, and those peaks basically just evolve independently as we warm up. But if we get a little bit closer, so we bring these peaks closer together in density and energy, then what we see is we warm up, just the resistivity peaks from those peaks, you know, features in our band structure tend to merge together. And that's telling us that something a little bit interesting is going on, right? So what we realize is that when we have two gaps opening up, you trap some states in between. And so you have to form some kind of little mini band in between those two secondary Dirac points. At low temperature, what you're going to do is you're going to put your Fermi level either here or here, and your resistivity peak is when you're inside this gap or this gap, right? So you get a strong peak here, a strong peak here. Nothing too extraordinary there. But when you warm up, now what you're going to do is you're going to sample states over a wider kind of thermally smeared energy range. And now the highest resistance is when you kind of capture both of these gaps, but also all of these states in the middle. And so we see a highest resistance up here. This is telling us that we have kind of very high resistance bands, which are flat, which are trapped in between these points. So I think, you know, this hasn't still, you know, has to be explored in more detail. But, you know, what it tells me is that we can create flat bands rather than by twisting two pieces of graphene, almost by making kind of magic angle twisted, you know, there might be a magic angle where we can twist two pieces of BN on top of on opposite sides of graphene and create a flat band in between these secondary Dirac points. Certainly, you know, this is having this resistance peak in the middle tells us that these are very low, high resistance states, which tells us that we have a flat band. Okay. Last paper, we're a little bit over time, but I think we're okay. So let me just tell you really quickly. Go ahead.
Just because you took a lot of questions during your talk.
I will blame the students.
Exactly, you can take a bit more time.
Excellent, okay. It's always someone else's fault. That's what I try to train my daughter. So, okay. Nonlinear optics of interfaces, right? So this is just a quick teaser. If we look at the nonlinear optical properties, we can actually start manipulating them by rotation as well, right? So let's see what's going on here, right? So what we're interested in is the second harmonic generation imaging of interfaces between two pieces of boron, two bulk crystals of boron nitride, right? So second harmonic generation, I think I have a cartoon here. Sorry, there's some failed animation there, but second harmonic generation, basically you hit a crystal with a certain frequency of light and you look for it to generate light at double the frequency. This requires a finite chi2 response of the material, and that, from the magic of group theory, requires broken inversion symmetry. So this is actually a strong probe of inversion symmetry. And if we see down here, if we have boron nitride, one layer has broken symmetry, 3 layers has broken symmetry, but 2 layers and 4 layers, etc., do not. So there's an odd even behavior here that emerges very quickly. So we can see this if we just look at a piece of bulk BN. So if we take this, this is about 121 layers thick, and we can get that with AFM, we can actually get within a plus or minus 1 layer. You know, when we look at the little kind of mini flakes that are sitting on top, we can see that those are steps that are either 1 or 3 steps thick in this sample. And now when we image this by second harmonic generation, we see a huge difference in the SHG signal when we're different just by 1 atomic layer, right? So that's telling us that going from odd to even number of layers changes our SHG a lot, right? So we've actually done a very careful study of the SHG intensity as a function of BN layer number. So the data is here, but what we see is that when we start at 0, we get 0, 1 layer, we get a strong signal, 2 layers, it goes back down, 3, it goes up. And so we get this odd, even alternating pattern. But what you can see is that actually there's a crossover. And now the odd even becomes even odd. And this was a little bit of a mystery that we sought to understand. And, you know, so we tried to do some theory here. And the basic idea is that you have to look at, you know, when we get to much thicker layers, why do we not just have this continuous odd even response? And the basic idea is that you have to look at the kind of gradient of the electric field going through a thick crystal. And so you have a quadrupole response instead of just the simple dipole response. So when you do this, if you kind of look at how the electric field varies as a function of position and the interference in your stack, you can model all of this very well with a transfer matrix model, right? So we can see that, again, kind of odd structures have strong SHG that then goes down and then goes back up, and even does the opposite. So this is actually nice because with SHG now, if we know that we're about, you know, let's say we think we're around 50 layers thick, we know SHG will be very different between 50 and 51. And so it actually really allows us to nail down exactly how many layers we have, because we can get that extra plus or minus 1 just by looking at which curve we're following. So now the question is, if we stack 2 pieces of boron nitride on top of each other, what do we get from this interface? And so this is where I go back to this issue of the kind of atomic alignment. So we're assuming that these interfaces find the lowest energy configuration. And so that's what we're putting a little bit of translation here. It seems to not really matter for the overall group theory of the problem. But so this is what we're going to try to understand, is now that we can understand the SHG from one BN slab, if we combine 2 of them, we're going to get an interface with broken symmetry. And how do we, you know, what happens there, right? So let's do a first simple experiment. We're going to take 1 piece of BN and we're going to crack it into pieces. And then we're going to stack the pieces on top. So we have identical numbers of layers on, you know, that we're putting together. Let's see. Somehow I'm getting questions in strange order here. Sorry, folks.
I think it's the time zones.
Oh, I see. Yeah. Okay. All right. But I got one at like 9:40. Yeah. Yeah. Okay. I'll try to keep on these as best I can, but maybe we can, you know, we're close enough to the end. We can maybe save them to the end too if it's not working right. Okay. So there we are, right? So we can kind of look at different cases. We can look at if we have odd stacked on top of each other, now we've made even. If we have even, we can make even, but now we can look at different rotation of this interface. So we kind of have 4 different cases here, and we can do this, right? So this is, you know, picking up. We can pick up a piece and actually only pick up part of it. So it's pretty amazing. We can actually, you know, kind of crack this crystal and then pick up 1 piece at a time and put them all together. So this is now kind of a stack made from 1 piece cracked apart and put together in different ways. And again, here's on the right, you can see the SHG image, and you can really see big differences between areas that are stacked in different ways. So let me just show you what we have here, right? So again, these are areas in area, so 3 is just the bottom BN, right? Area 2 over here, we've stacked the bottom and top at 0-degree alignment. So we've kept the same alignment. And area 4, we've stacked but rotated by 60 degrees. And you can see again, just that, you know, when we stack with 0 degrees, we're actually suppressing the SHG. When we stack with 60 degrees, we're strongly enhancing the SHG, right? So that tells us that the interface does matter. And we still have to consider all of these bulk contributions as well, right? So again, this requires a bunch of modeling. And what we're really interested in is, you know, can we engineer a situation where we see the most signal from that broken symmetry interface when we do that 60-degree rotation. And kind of our contribution from the background is suppressed. And so, you know, if you go back to these curves over here, where you want to be is you basically want to start with a piece that, like if we start with a piece that's about 70 layers thick, and then we stack two of them on top, now we get to 140, and we're going to get very weak SHG intensity. Right? So that's the basic idea. Or if we start with a, I mean, I think that's the simplest example. So we can kind of do this, right? We can, you know, kind of see where our sweet spot is, right? And we can see that this enhancement factor, when we go to total, so we don't now have to stack the same numbers. We can, you know, have different n on the bottom and the top. But if this n total is around 150 and it's odd, then we get strong enhancement. If n total, you know, we basically have completely suppressed the bottom or the bulk. Likewise, if we have kind of even, such as like 64 and 164 and 4, well, so let's see. Yeah, this is n bottom is 164, and then n, I think this should be n top is also 164 anyway. So you can see that we get a strong enhancement, you know, basically zero contribution from the bulk when we have total n of about 300. Okay, so now of course we come back to our AFM and we start pushing pieces of BN on top of other pieces of BN. And this is where this stickiness comes in a little bit in a more interesting way, because when you have two of the same material, once you get to alignment, now you've created a bulk crystal of the same material, and it doesn't want to rotate anymore. It strongly adheres, right? So we kind of push, 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 and then what we find is once they get zero alignment or very close to zero, it locks, and the tip ends up just dragging over the top BN. Right? So we can, and you know, we can see, so we make a bunch of these little rotators and we push this one until it locks, and we can see that it actually aligns quite well with the edge of the bottom boron nitride. And this one is aligning, we push it in the other direction, it aligns 60 degrees off. Right? So these things really do align with the crystallographic axes of the boron nitride. So, you know, it's just another example, right? We basically push all the way through either to the left or to the right. So if we have a bunch of these kind of at an intermediate angle, all of these end up being aligned at either 60 degrees kind of with this edge or 60 degrees away from the edge like that. So that's our locking. This immediately tells us what our crystallographic axes of our bottom boron nitride crystal are, which is kind of nice. So again, now we can take, you know, we can lock two at 0 and 60. That defines our axes. And now we can rotate in between. What we find is that we can take each one and we can rotate it to locking, and then we're stuck. So we end up doing, we rotate one clockwise, and then we take another one and we rotate it counterclockwise. And so we can basically explore kind of either between 0 and 60 or going in the opposite direction, 0 and minus 60, but we can't keep going over the hump like we did with graphene and boron nitride. But again, what we can see is that our simple transfer matrix model can reproduce this data not only as a function of how many layers we have in the stack, but also as a function of twist angle as well, right? So we can see that in some devices, we get a very strong modulation as we go to this A-B stacking. In other devices, we get much weaker modulation because we're getting a much stronger contribution from the background. Just a couple other things really quick, and then we can wrap up. We're also seeing that this operates over a very broad energy range. So this is not relying in this energy range over, it's not relying on any kind of resonance, although we do see it's starting to pick up at higher energy. This may say that we're hitting, you know, interesting band structure modifications of boron nitride. We need more lasers to get to higher energy to look at this. And just the last thing is that we can start using this SHG signal now as a probe of the buried interface, right? And so again, we can do some kind of PowerPoint physics. We can look at that rotation angle between the two layers of BN at the interface. And we can look at the angle that that Moiré pattern is making. And then we can measure the polarization pattern of the second harmonic generation signal. And we find that the second harmonic generation signal very closely follows the angle, the polarization angle from the Moiré pattern. And you know, if you kind of look at the group theory of the problem, that all makes sense. So of course, you still have to look at the interference between the interfacial SHG with the bulk SHG. So you know, you have to do a little bit more complicated calculation, but what we're finding is that, you know, here's the kind of interfacial angle, the total, when we kind of add that up with the bulk contributions as well, we get a model that fits the data very, very well, right? So we can really understand this kind of SHG symmetry angle as a function of the rotator twist angle. However, when we get very close to alignment, things are not quite so beautiful, right? So when we zoom in here, what we find is that, you know, we have data that fits this curve pretty well, but then, you know, within 1 degree or so, we see this kind of flat behavior, right? And so this is where we have something else more complicated going on. We have some reconstruction, we have some local strain, don't know exactly. But this is certainly telling us that we do not have the simple Moiré pattern that we get from just rigid rotation. And so I think, you know, this is very nice to have this kind of optical probe of a buried interface. We can start to understand that its properties are not what we expect from a simple model, and we have to think about it more carefully. Last thing we can do is now, with all of our understanding of the bulk and interfacial response, we can actually start stacking crystals on top of each other to make kind of quasi-bulk crystals that have strong nonlinear properties by looking at kind of the interference between all of these different interfaces. And, you know, we can see that by stacking a few pieces on top of each other, chosen with the right thicknesses, we can get very strongly enhanced second harmonic generation. It follows a roughly quadratic behavior with a number of slabs at the beginning, then goes more like linear behavior because, again, we have this interference with the bulk, which starts to become more dominant. I think, again, there's a lot to build on here. I think really careful if we look at kind of resonances at frequencies that are commensurate with the stacking, or, you know, wavelengths that are commensurate with the stacking periodicity. Could be very interesting, making something like a second harmonic generation Bragg mirror. Also, as was mentioned, if we start looking at twist between the layers, you know, can we get chiral behavior, especially as we stack more and more of these on top of each other? So, you know, as we start getting, as we continue to get better and better at stacking and assembling and modifying these crystals, we can really start thinking about some kind of program structures that you couldn't possibly hope to do, you know, in bulk materials. So there's, let's see. Yeah. Questions are coming in funny order. So I think that's the end. Let me just mention, so there are a lot of collaborators here, but let me just mention the kind of the leads on the different projects. So the first project was led by Tarun Chari and Ken Shepard's group with Rebecca Ribeiro, who was a MERSEC postdoc fellow. The Moiré rotation was led by Rebecca Ribeiro and Julia Zhang. A collaboration mostly between my group and led by Corey Dean's group. This symmetry control project was led by Nate Finney and Matt Yankowitz, again with mostly with the Dean group. And this nonlinear optics work has been done with Kaiwan Yao in Jim Shuck's group. So, open for questions.
Thank you very much, Jim. So let's indeed go to the questions that were already in the Q&A. You want to try to find them in the right order? I also lost track, so.
Yeah, it's showing me that there are more, but I'm still getting the same one at the bottom of my queue. So I went from 23 to 26, but I'm still seeing the same ones at the bottom. All right, so let me just, here's a new one. Can we build these nonlinear crystals out of TMDs, or is there something special about BN? No, in fact, we absolutely can build these out of TMDs in the same way. Other questions, do we have a paper? So I sent papers on a couple of the areas. I did not send the paper on SHG and HBN because it's under review right now. But I think, let me check if we might have posted it to archive, but I think, you know, we may post that to archive soon anyway. Would the integration of a magnetic material and the rotator be possible in the setup? So, you know, I have lots of dreams about ways to control this rotation that don't require AFM. And I'm hoping to write grant proposals based on that this summer. So I think it's super interesting, right? Can we make dynamically, can we do dynamic manipulation of structures in situ? One of the issues, of course, it would be wonderful to do, to have a sample cold and change the rotation angle, right? And, see all the crazy, superconductivity emerge or something, right? Things get really sticky at cryogenic temperatures. But, it may be possible. We're working with Dmitry Basov's group that have, they do low temperature near field optics. And, so you can use the near field tip also to do this rotation. We've managed to do it at 77, but not all the way down to base temperature yet. Some other questions. Where are we? There's my. So we're going back to the original. Let's see. Question about why there's in the very first paper, or very first talk, when we showed that there was a kind of a quasi-commensurate angle when we had a little dip in the resistance, there are, this is a very good question, there are other commensurate angles where we don't see a resistance dip. I don't think we understand that yet, is the honest answer. Let's see, other things. So in some of the experiments, we're putting a layer of HSQ on top of the HBN. Does that change the intensity of a Raman signal? It doesn't seem to. It's transparent. I think it's like 30 to 50 nanometers or something like that. I don't know exactly, but and we can do experiments without the HSQ. Also, sometimes we can build a ring of HSQ around the edge if we want to have a thinner area in the center. We're playing lots of games like that. So we can take questions by hand raising also, I think.
Yes, so if you have any more questions, please raise your hand and I can allow you to talk. It's a long list, so I have to scroll down. Please don't hesitate to raise your hand. In the meanwhile, I will, oh, there is already one. Christian, of course. I will allow you to talk.
Hi, so thank you for the talk. It's very interesting way to measure. And I had a question about one of the plots that you have shown when you measured the resistivity of the secondary Dirac points versus the temperature while extracting the Arrhenius plot.
Yeah.
So there is some funny feature in one of these plots I wanted to ask. Because there is a peak in resistivity at some finite temperature that is higher than your base temperature. Yes, here.
Yeah, yeah. Yes. So I think, I think it's fair to say nobody has a great understanding of the details of these plots. So if you go to very low temperature, for instance, we all think that this is some kind of transition to a variable range hopping behavior, but at least in the very high quality samples, I haven't seen it done beyond a hand wavy way. I would be very interested if anybody wanted to look at that in more detail. We are continuing to work on a paper that is, you know, as I say, that it's been in rejection for a while, you know, instead of in press. But we've been looking at in gapped bilayer graphene. So just simple Bernal bilayer graphene. You have incredibly strong signatures of electron hole scattering near charge neutrality when you have thermally excited electrons and holes. And so this, at the higher temperature scale, it dramatically changes the functional form of your resistance versus temperature. And you don't follow simple activated behavior anymore. We think probably some of that is going on in these samples also, even though it's not bilayer, you still have a gapped system with a, you know, something like a parabolic or a hyperbolic dispersion. So, you know, I think it's a signature of some funny scattering going on. Of course, you know, in any kind of activated behavior, when you're going to temperatures that are well above the band gap, now, you know, you should expect it to transition to a metallic behavior. So forgetting hydrodynamics, you know, if you just had an activated semiconductor, you know, but you're at temperatures well above the band gap, then you're basically, just from your thermally excited carriers, you're basically a degenerate metal, and degenerate metals have, you know, conductivity that goes down with increasing temperature, right? So, you know, it just shows you that you don't have kind of a constant scattering time, and your temperature dependence is completely just, you know, counting the number of activated carriers. There's something else going on.
Okay, great, thank you.
Let's see, are there more hands up? We still have 3 minutes. I have a question about the flat band. I'm not sure you mentioned it. Do you know what's the bandwidth of the flat band? Is that theoretically?
Well, I think you can, where was that? You know, I think you can get it pretty easily. I mean, if you basically just take the separation, I don't have a number on top of my head, but if you take the separation between the two Dirac peaks, you know, maybe you have to subtract the band gaps also, right? That's basically your bandwidth, right? Okay. So I think it's not as flat as the flat bands in twisted, you know, in the magic angle, but pretty flat.
And a well-defined controllable gap, so.
Yeah, yeah. And, you know, we could certainly go to, you know, because we can take these two peaks and we can bring them very close together, right? And, you know, in that case, you should be able to flatten your band. I mean, then you have to worry about disorder broadening, and then, you know, whether, again, when we bring the two bottom top BN together, you know, very close, is there going to be any kind of snap to alignment? But it, you know, it may be a system that is a little bit easier to control than twisted bilayer, because it's, you can achieve it by twisting two thick rigid structures rather than two very floppy structures.
Yeah. It's still not so easy that you can make centimeters of it, but okay.
No.
We'll see another approach of making flat bands.
Yeah.
Okay, I don't see any more raised hands, and we are now at the end of the time. Jim, this was a fantastic talk. If people were in the room, they would give you a very loud applause. So on behalf of all the attendees, I want to thank you very much for this fantastic educational talk, a fantastic overview of the state of the art. So I hope you will stay online for the other talk, and and for the rest of the workshop. So all the attendees feel welcome to reach out to Jim for any more questions.
I will try to be, I'll be here for the next talk, and I'll try to be in and out. And if not, I'm taking care of kids this week, so as well. But you know, reach out by email, and you know, Frank knows where to find me. So
yeah, absolutely. Okay, great. Thank you very much.
Thank you all.
The audience for being very active with asking questions.
Thank you very much, Joel. I'm gonna finish the meeting now. Thank you, Jim, and see you in the next seminar. Bye-bye.